Hi, everyone. I think we can start now. Thank you so much for joining our live stream. My name is Anya. I'm a business development manager of K-Mine. Also here with me, Eugen Chernechenko, one of our engineers who will answer your question at the end of the stream. Eugen, do you hear us?
Yeah.
Perfect. Perfect.
Hi, everyone. So I hope you will ask us many interesting questions.
Perfect. Well, let's dive right into the agenda of today's stream. As usual, this stream is being recorded. So if you need to leave in the end, or if you know anyone who might be interested in this functionality but couldn't join today, you will be able to send them the recording link later on. And I mean, if you follow us for a while, you know that we do have 12 models that we released for open pit and for underground mining. So today we are reviewing our pit optimizer model, more specifically its new capabilities. I mean, if you attended our very first stream, you might already know that essentially the pit optimizer model is a strategic planning tool for a mining engineer. And as you know, the main goal of planning is essentially to define business strategies. So to see if you can increase cash flow and the company's profitability. That's the #1 task for mining companies. And the management needs to agree on strategic tasks and determine development benchmarks before throwing significant resources to the mine site. Usually, if all economic parameters are stable, the enterprise is needed to review and redefine these benchmarks, and it's better to do it every year or so, because you need to see if there are things that need to be adjusted, or you need to make sure that everything is right on track, right on schedule, so to say. And at the end of this planning stage, a mining company should have a clear and defined optimal pit limits, so it can split them by intervals and by volumes. And I'm not even mentioning how many issues can be solved during this whole process. So what we are reviewing today is the actual factor or actual factors that affect the parameters of the final boundary. We will apply a sensitivity analysis of pit walls to different variations of basic parameters, and we also want to take a closer look at the economic consequences of any changes in cutoff grade. Our goal today is to show you how our pit optimizer can help you to analyze the pit wall sensitivity if you want to play with these few parameters. Speaking of the parameters of sensitivity analysis, you all know that when you search for the final boundary, you need to constantly evaluate all elements of the block model. It's necessary, so when you actually do sensitivity analysis, you can select the main indicators and assign them different priorities that would affect the cost of each block. So for example, if we set the durability of pumping equipment as one of the indicators, we can calculate the impact on mining costs per 1 ton of rock mass. So what we will see is that the impact will not be that substantial in comparison to the durability of the main equipment, which means we can play around with these indicators. The main question is which parameter or which parameters would be crucial for profitability, and is it worth the hassle for the mining company to allocate all the resources on the site? Obviously, the company that initiates this process should have a detailed plan as some sort of guide that would help them to make strategic decisions. So When we create final boundaries in the open pit, we do need a few source data sets. One of the main ones is the block model with the basic parameters such as block coordinates, block sizes, density for each type of material, material class attributes, and quality parameters of the available component. The other type of source data is economic parameters like mining, processing, and transportation costs, and the final price of all product types. And the last type of source data is mining conditions, like the angles of the pit wall slope, stop width, cutoff grade, and so on. Obviously, we need to make sure that the values of these data sets are as accurate as possible, so our planning results would be as reliable as possible. So if we are going to consider the actual example, we are taking the block model with all required source data that I mentioned earlier. Obviously, all data in our stream is created artificially, so we can demo you the process. So please keep it in mind. But our block model here, it has regular block size of 10 by 10 by 10 meters. So to create a basic scenario, we will use different mining costs for various rock types and different transportation costs. Let me just share the screen. Okay, perfect. So we will use different mining costs for various rock types and different transportation costs depending on the elevation height. So we are using several processing costs for both types of ore. Rock type number 2 corresponds to high-grade ore, and rock type number 4 corresponds to low-grade ore. The data in the table are used to determine the net present value. So since our example uses data where capital mining operations are performed on the ore body disclosure, let's assume that this small open pit is operating with a capacity of 1.85 million tons of ore per year. Also, we would set our expected price adjustment coefficient as 1.6. So in the end, we will compare all results for all scenarios by this coefficient. All of them must be reasonable and comparable, and we are setting cutoff grade as 16%, which is the same as the majority of Eastern European deposits. So in order to start the scenario, we go to planning and optimal pit boundaries commands. In the dialog box, we're creating a new scenario. And we specify the name and the path to the location of the current project main files, and we add a block model that will be used. It's already loaded in the current file, so let's name it and select it in the layer editor. It's in the folder with the project. So we see that the software offers to create additional file for the block model. Basically, this file adapts the selected block model to work in the pit optimizer module. And we start identifying, so we start with identifying the price adjustment coefficients. We set them from 0.6 to 2 with a step of 0.2. And we're adding 3 as an additional factor to see the open pit potential. So let's name this scenario. And if we need to, we can always leave the notes there as well, as you can see on the screen. Yep, so then we can move on to the block model settings in the rocks field, and we select the rock type attributes. In the block weight field, we select the specific weight. And in order to display all the data, we'll have to use values with 1 decimal sign at 1 million scale. Then in the wireframe settings field, we select the pre-configured settings to display all the surfaces. Perfect. And you can see the general data about the dimensional information of the block model in the general information menu. The data of mine rock type menu contains information about rocks within the material class attribute. So the information with 1 decimal sign is provided in millions. The next step is to configure the angles of the pit slope, and we can simultaneously review the offered functionality. The number of benches from a slope parameter affects the way the final boundary is constructed. So the steeper the pit wall slope angle, the bigger value of this parameter should be set. So we can specify it as 3 to the current conditions. And there are 3 methods that are available to set the angles of slope. The first one is to set them by area. The second method is by vector, and the third one by properties. All these methods are based on azimuthal approach, and then the vector method appears to be the most fundamental, as you can set different pit wall slope angles for directions, and overall all methods of slope angles are based on this method. The by property method uses data from the block model. So you need to specify the material class attribute, default angle, and select the required rocks from the provided list. So in our example, let's set the angles of slope by area. And in order to do that, you need to create them first. Under existing conditions, these geotechnical areas must be identified by geotechnical experts. So in this example, we will use construction of polylines, and we are expanding them so we can get the required result. So let's create 4 geotechnical areas. Using the extrude wireframe commands from wireframe menu, you can create solid wireframes for all areas simultaneously. So the selected parameters ensure that the future open pit will be completely covered by wireframes. Now let's create the corresponding layers and place new geotechnical objects to use them in the future. Perfect. So next we need to select the appropriate wireframes as filters for each areas. And we need to save the settings so we can use them later. And basically then we need to repeat this action for each of the 4 areas. So after that, we adding geotechnical areas, and we also hiding their visibility so it will not distort our open pit image. Okay, we're basically just repeating here. So once all the areas are added, we need to set the angles of the pit wall slope. For zone 1, we're setting the angle as 45 degrees. For zone 2, it will be 40 degrees. And for zone 3, let's set it as 35 degrees. And for zone 4, we're setting it as 50 degrees. For all the areas that are not covered by wireframes, the default angle would be 42 degrees, but it will not be used since they created geotechnical wireframes cover the open pit. So the next step is adding the final product's name and its cost. We leave the property and the property type fields empty, as these settings are required when the block model has a field with specified values of the valuable component grade in the output product. So we specify cost as $100 per 1 ton of concentrate. And now let's review the processing settings. As was discussed earlier, rocks number 2 and number 4 are ore from the attribute of material class. And we are assuming that the rocks with rock number 2 are easier to process. So as a result, fewer resources are used, and the cost of processing of 1 ton of ore would be $15 per ton. As for rocks with the rock number 4, let's assume that low-grade rocks require more attention and it will be more expensive. And we specify cost as $18 per ton, and we set parameters for losses and dilution as 2%. So now we can define the yield. Since our deposit is created artificially, we will use a theoretical formula to determine this parameter, and the formula contains only 3 indicators. It's reserve grade, recovery grade, and assay of tailing. And we're selecting the ferrum total attribute as the reserve grade and recovery grade of 65% and tailings of 10%. And as a result, we will make the concentrate yield dependent on the ferrum total. And the final step of the current settings is to set the cutoff grade. The material class attribute rocks number 2 and number 4 will be processed, and they have a magnetite indicator of more than 16%. The rocks with magnetite content less than 60% will be considered as waste. So now let's configure production and transportation costs. In the corresponding menu, we select a rock group of similar mining costs. Mining cost for ore is $6 per ton. Rock waste is $5 per ton, and soft waste is $4 per ton. Mining costs for ore also often include a royalty tax or other typical production costs. That's why the mining cost for ore is usually higher than for waste. And the soft waste has a minimal of mining costs, as it doesn't require preliminary blasting. And the rocks with material attribute number 100 serve as a constraint to develop the open pit within this boundary. So let's enter a higher mining cost, so these blocks will not be involved in the mining boundary. So the next step is to establish the transportation cost of rock mass. Let's say that the transport equipment is selected correctly, and regardless of the bulk density of rocks, dump trucks will be loaded nominally. And in this case, the transportation cost for all rocks will be the same. Let's set them according to the elevation height. For rocks with material class attribute number 100, we will specify a high cost value at all intervals. Perfect. So the capital cost tab shows capital and other costs for each specific year. You can automatically calculate reclamation costs in several ways, and all this data will be considered as negative values for the profit. And now we need to save the project, and after we're done with the settings, we can run the calculation to determine the optimal pit boundaries with the specified parameters. And in a few seconds, the message on the screen informs you that the calculation is completed. So now let's review the calculation results. For a price coefficient of 0.6, the number of blocks to extract is 415. That means that mining operations will not be profitable under the current conditions, and the ore uncovered from the waste is mined and the open pit is considered finished. As the price is adjusted, the number of mining blocks increases, and when the price increases for the final product, the volume of extracted rock mass increases as well. So the engineer needs to determine how much the coefficient increases and which price adjustment factors should be selected for further activities. It is the most crucial step because it will define the open pit scope and potential, and therefore basically the company's opportunities. Typically, engineers use parameters like profit, profit factor, profit margin, income, net profit value, and quantity of mined ore. And depending on the requirements, other indicators also might be applied. But in our example, we want to see how the different values influence the final boundaries of the open pit. So let's simplify and specify the boundary with a coefficient of 1.6. We'll apply this price adjustment factor for all future calculations and compare the final results. So the calculation results can be displayed as individual sections, which you can hide during the visualization of the block model. And you can hide the blocks in the block model that are involved in the processing of the selected boundary. Also, the results can be uploaded as a surface. Let's not forget that according to the attribute of the rock type material class, different colors display different rock types. And we will take this scenario as the basic one. It will help us to compare all future scenarios. Perfect. So let's configure several scenarios with different source data. We can start our sensitivity analysis with the mining cost and transportation cost parameter. What we're doing is increasing the cost parameters by 30%. I mean, it's best to perform this analysis many times with smaller steps, for example, 5 times with a 5% step. But we review it with the 30% analysis step for all variables, just for demonstration purposes. In order to structurize different scenarios in the project tree, we name them and leave notes, and we specify the mining cost as 6.5 for all hard rock waste, and 7.8 for the ore, and 5.2 for the soft waste. And we're leaving the rocks of class 100 alone, as their inflated value does not require any changes. So the transportation cost increases by 30% as well. This analysis can also be considered separately for mining and transportation costs. But in our example, we would like to highlight the main aspects of sensitivity analysis and demonstrate you how easy you can do it in K-Mine software. Okay, we're clicking OK, and in a moment we can take a look at the results. Perfect. So we can see that when the cost increases by 30%, the number of blocks for mining significantly decreases in each of the coefficients. And we can create another cost scenario in the project tree and name it. And we indicate that the costs are reduced by 30%. Okay, so we're basically doing the same. We leaving the rock class with rock of class 100 alone. Okay, perfect. So when you see the results, you will actually see that the open pit with the price factor of 1.6 has significantly increased. So we can preliminarily argue that under these conditions, it is reasonable to reduce the money and transportation cost of rocks to increase the profitable durability of the open pit. So this slide provides three shells that we got from all of our activities, changing the money and transportation cost of the rock mass. We see, when we see all three scenarios, it's obvious that the scope of the open pit depends significantly on the money and transportation cost parameters. The applied data is arbitrary and the deposit is artificial, so this provision will not be applied to all open pits, but the worldwide practice shows that the mining cost does affect the sizes of the open pits, but not as significant as the cost of the final product. And we will return to this issue after we get the next results. The line that helps to construct a section is drawn in the center, so we can study the obtained results more precisely. So the section displays how the cost factors affect the size of the open pit. The mine open pit boundary with the price adjustment coefficient of 1.6 and 30% reduction in the cost of mining operation is indicated in with green color. The basic scenario is colored in blue, and the increased cost of mining operations by 30% is highlighted in red. As you can see, the green boundary is significantly different from the red one, but at the same time, the red boundary is not entirely different from the blue one. What basically means is we need to consider each of the mining cost parameters in detail. A slight increase in mining cost will not significantly affect the mine boundaries of the open pit, but when the mining cost changes in the opposite way, the result will have a significant positive impact on the production value. So when you finally review all the scenarios, we can compare the values of the parameter in detail. Now let's review the following group of source data for the scenario. In this case, we will check the processing cost effect. Comparing to the basic scenario, the data that will be changed are highlighted in the frame, and the other parameters remain the same. I mean, it's important to compare results in which only one type of parameter will be changed during the analysis, because if you change several parameters, it will be difficult to notice the impact and understand what exactly affected the result. Okay, so we create the new group of indicators and leave notes. And we specify the processing cost and increase it by 30%. For high-grade ore, we specify the processing cost as $19.2 per ton. And for low-grade ore, we set it as $23.4 per ton. And we can save the project and start the calculation. So the results demonstrate that the open pit with a specified price adjustment factor of 1.6 is not essentially different from the basic one. We can make sure of this, and let's do a similar task only with the decreased price and see the result. We can upload the surface and save it in the appropriate layer and continue working. Now let's add the next cost element to the project tree. We name it and leave notes. And we specify the processing cost for high-grade ore as $10.5 per ton, and for low-grade ore, we set it as $12.6 per ton. And let's save the project and start the calculation and look at the results. So at a glance, the changes are visible, but the question is how significant they are. It's obvious that there is a difference, but it's not that essential. Let's look at the results more visually, save the surface and display all three surfaces in the section. Now we can say that there is a difference, however, it's insignificant. We can take another look at the results of the section construction. And the section provides the difference between three surfaces. Obviously, the lower the processing cost, the more profit the company will obtain in the future. At the same time, the influence of this indicator on the final boundaries of the open pit is insignificant. So in the next scenario, we will see how the change of the price for the final product affects the size of the resulting open pit. We can leave the rest of the parameters the same as in the basic scenario. And similarly to the previous scenarios, we create a new cost element in the project tree, name it and leave brief notes. And in this scenario, we consider the impact of increasing the final product cost to the level of $130 per ton. Perfect. So now the result is obvious. We see a significant expansion of the open pit, which is practically touching the restricting blocks. Upload the surface and we save it to the appropriate level and start the next scenario. Now we create an element in the project tree. We name it and also leave brief notes. And next set the final product cost as $70 per ton. And we can take a closer look of how the optimal boundary is calculated. So according to the blocks to be mined, it is evident that the final product cost affects the parameters of the extracted open pit essentially. Now, there is the mining cost and the final product cost. Later, we will see which parameter has more crucial effect and what would be the results of a detailed analysis on the economic parameters. So let's review the top view with all three scenarios of the final boundaries displayed. You can see that the difference is really substantial. And let's look at the section. The same concept as for the mining cost indicators is applied for the section. If the final product value increases, the open pit will significantly increase and extend its mining period. Reducing the price, of course, will affect the size of the open pit, but not as significantly as its increase. And the total changes of the open pit size are more than essential. We'll see the results of the export data analysis in the end of the stream. And the last parameters for sensitivity analysis is cutoff grade. And let's look at how the open pit size changes under 12% and 20% of cutoff grade. All other parameters are similar to those from the basic scenario. So we're creating a new item in the project tree. same thing, we name it and leaving the notes. And first, let's review the scenario where to define or the cutoff grade will be 12% and look at the results. So as a result of the calculation, the open pit is widely expanded. Now let's see what results will be in a similar scenario, but with the cutoff grade increased to 20%. Perfect. So increasing the cutoff grade by 20%, you can see that the open pit size has radically changed. Of course, it is logical when the boundary that is separating the ore from the waste rock increases as the open pit decreases and vice versa. But in this specific presentation, it is important to review how much the open pit boundaries change. So let's take a closer look at the top view. The difference between the scenarios are visible and notable, and the impact is significant. Look at the section. You can see from the section that the west pit wall is quite different from the previous scenarios, and a decrease in the cutoff grade parameter found a lot of low-grade ore that has to be processed. Of course, more ore is excellent, but we understand that we need either particular processing technologies for lower quality ore, or its processing would become more expensive, or the quality would not be maintained. So in general, there are specific criteria for evaluation, but in our scenario, we decided to determine different processing costs for two types of ore. So by looking at the economic indicators, we can answer our questions. So we can get some information by exporting from the optimal pit boundaries menu. As you can see, all the basic information is available for detailed analysis, and all these weights and volumes for all primary rocks, economic parameters such as income, profit, expenditures by group, and so on. All this information is also available after exporting, for example, if you export it to Excel. So now let's review the charts and figures of the source data in detail. If we do it for each of the scenarios with the main parameters, we can decide the most affecting factor from those that are provided in the table. So first we can select the optimal boundary. And in order to do that, you should start eliminating the scenarios with minimum amounts of rock mass excavation, as all mining companies aim to extend the deposit durability without losing in profit. So let's eliminate the scenarios that contain reduced final product cost, increased mining cost, and cutoff grade. The scenarios involving a change in the processing cost are also being eliminated among the other scenarios. We will not review them. So now there are three scenarios left. The first one contains increase the final product cost. The second involves reduced cost of mining operations. And the third one consists of the reduction of the cutoff grade. The cutoff grade scenario is less important than the other two, and there are two scenarios with approximately the same indicators. They will have the same open pit durability and approximately the same volume of mined ore, so it would be difficult to conclude which one is better. But given the economics chart, we can focus on the second chart. There you can see that the income and NPV is much higher for a scenario with the increased final product cost. So now we can go back to the sensitivity. In order to do that, we need to look at the peak values of the indicators for mining the total rock mass. We already identified two optimal scenarios. Now we can pay attention to the peak minimum values on the rock mass. The increased mining cost scenario is 59.2 million ton, and the reduced final product cost scenario is 36.5 million ton. It means that in terms of volumes of mining rock mass, the final product cost parameter will affect the final boundaries of the open pit the most. It is also evident that if we look at the peak values of cash flow, the result would be similar. Obviously, we have no control of the over the product cost on the global market. It really depends on many interrelated global factors, but what we can understand is the potential of the open pit and if there is an opportunity to increase volume of waste or if it makes sense to hold it back. In most cases, the difference in the results in sensitivity analysis between the mining cost and the cost of the final product is leaned towards the final product. So maybe the artificial prices are slightly inflated and their influence is blown out of proportion. But we can finally review the last chart where we got the results that help to make a preliminary prediction for transitional values of the data variables. It also helps to answer the question of what should be the mining cost to make a profit level of $800 million. Or, for example, what profit would you get by reducing the processing cost by 15%? Of course, the results would be more accurate if there are more scenarios, but we want to show you an example of how you can get the sensitivity analysis by tinkering with these criteria and these parameters. If you do strategic planning, it really does help to make the most reliable and accurate estimation, especially when it comes to the question of whether to mine or not to mine, or when you should mine and for how long. Okay, so I think that's it. We'll see if we have any questions here. I want to give the floor to Eugen as he's the one who would be answering questions. Eugen, do you hear me?
Yeah, I can hear.
Perfect. So I see that the first question is which algorithm is running the optimization?
Thank you for question. So we are using upgraded Lerch-Grossman algorithm.
Perfect. So the other person asked what kind of coefficient mean in this model? I guess just what coefficient mean in this model?
So this is a price adjustment coefficient. We set them at the beginning of the scenario from 0.6 to 2 in increments of 0.2 and 3. This coefficient is multiplied by the price of the final product.
Okay, I think that's basically all the questions we have right now. You can send other questions later on. We will answer them on our LinkedIn page. And I think that's it. Thank you so much for joining. We will send all the attendees the recording of the stream. Please comment your feedback about the stream below and we can take it into consideration for the next time we live, and don't forget to follow our LinkedIn page. Hope to see you guys in the next stream. Thank you so much, Eugen. Thank you so much, everyone who joined in. I'll see you next month. Bye.
Thank you. Bye.